Welcome to TechnorazziLIVE, the program that lets you ask questions of metrology experts. I'm your host, Dirk Ducharme. Well, when I say Carl ZEISS, what word comes to your mind? Well, if you're like me, the word is precision. Precision optics, precision 3D measurement, precision form measurement, precision surface measurement, precision pretty much anything. Well, we're at the Carl ZEISS Technology Center in Brighton, Michigan today to take a closer look at a couple of ZEISS products. The first product will be the Calypso Metrology software. And in particular, we're going to look at how, with Calypso, you can create a measurement plan using one type of 3D metrology equipment from one manufacturer, take that measurement plan over to a different type of 3D metrology equipment from a different manufacturer, run that measurement plan, measure apart. So two different types of 3D metrology equipment, two different manufacturers, but only one software program. And then we're also going to look at CT scanning. In particular, we're going to look at the Metrotome from ZEISS. We'll see what CT scanning is, how it works, some typical applications, and in particular, what the Metrotome brings to the market. So to get started, I'd like to introduce Scott Lowen. Scott is the aftermarket manager for Carl ZEISS Industrial Metrology. So Scott, Calypso.
Yeah, Calypso is a software that ZEISS developed back in 1997, initially for ZEISS machines. And over the many years of success of that, and through some customers requested, we started to develop interfaces for other machines beyond the ZEISS products. So machines like Metatoya's, Brown and Sharp machines, LK machines, the Faro arms, Romer arms, and so forth. So we've just created direct interfaces to these machines with the Calypso software.
And what was kind of the driving force? What were you hearing from your customers? Why did they need a piece of software that would interface with different machines, different applications?
There's a few reasons, but one of the bigger ones was just a common software product. Someone who had a particular machine and built a measurement program for that machine. They didn't want to rewrite a new measurement plan on a second machine. It was a redundant of work, and not to mention it was just more efficient as far as training people and utilizing one common software.
And I imagine another reason might be if you had you'd written measurement plans or whatnot, and now your piece of equipment is obsolete, or you want a newer piece of equipment that maybe is more accurate, or an upgrade, that type of thing?
Yeah. Machines, the CMMs themselves, mechanically may be suitable, accurate, or whatnot for the actual customer, but the software becomes outdated. So just a standalone machine by itself would be well suited for a software upgrade. Calypso has interfaces for about 90% of our machines here in the U.S. So it would be an ideal product to improve efficiencies for that company.
Well, before we have you start Calypso, let me just remind our viewers, if you've watched our program before, you know the drill. Anytime during the show, you can send your questions to techno-live@qualitydigest.com. You see it on the bottom of your screen. It's also underneath your player. So send your questions, techno-live@qualitydigest.com. We'll answer them on the air in a couple of different, during a couple of different time slots during the program. Once during this presentation, once during the Metrotome presentation, and maybe even kind of a roundup towards the end of the program where we'll have both Scott and our next presenter up at the same time. So go ahead, Scott.
Yeah, I'd like to show you a little bit about the Calypso software itself. Right now I have a measurement plan that's already open, and if I have a CAD file, it's a lot more efficient to work with that. It inherently has all the CAD data to that. Calypso does support all of the major CAD vendors of CATIA and Pro-E, so forth, as well as the neutral ones of IGES and STEP. Right here I have an ASYS CAD file, and as I bring that in, this model is to my benefit, has all the nominal description to it. And as I was going to create a measurement plan, what I would do is start creating certain characteristics that I'd want to report. So the more common characteristics I have is icons across the top, something like a perpendicularity or parallelism, diameters, and so forth. These things are actually objects, just visual objects I'm creating. And as I open them up in Calypso, I can just pick the geometry that I want to calculate. In this case, perpendicularity between this top plane and this front plane.
Okay.
I can add a tolerance to that, and accepting it will set up a perpendicular calculation.
Okay.
And as I go through these, parallelism maybe, this top plane down to the bottom plane might be another characteristics we want to report. Diameters, maybe this top diameter if I have a bunch of these, I can just arrow down, indexing through all the characteristics that I want to report. So you can see it's pulling off the nominal definition here, 50 millimeters off the CAD file. And accepting those, I've starting to build my measurement plan for this part here.
So these are the parts these are the features that we're going to want to check at a later date.
Yeah, I'm especially preparing myself as to what I want to report. So if I want to use the arm, for instance, to measure all of these, I can highlight all 4 of them. And with that, I can prompt the arm here to start capturing data. It's highlighting the model for me. So right now, it's capturing data on this front plane.
Now, I notice as we're capturing this data, on the left-hand pane here, we're seeing the actual measurements that you're taking. Is that right?
Yeah, so right now I've taken about 600 points. It's telling me some form error that I might have had with the instrument. And then I can just accept that, and it'll ask me, index to the next plane. So to calculate perpendicularity, it now needs information on the top.
Sure.
So with that, I can move around here and capture 740 points. Accepting that, it's just going to start walking me here through the measurement plan. The next thing was parallelism. It's already measured the top one. I don't need to repeat it, but it does need some information down here at the bottom. So with that, it'll just kind of walk me through the rest of the program here. I need some points for the cylinder at the top and some more points down here at this cylinder. So that's basically what we would do to capture data. From there in the Calypso software, we can bring up a measurement report. Stuff out of tolerance is shown in red, stuff in tolerance is green. And Calypso has many different formats that we can output with that. But basically what I'm really trying to demonstrate here is we don't have a scriptic type language to Calypso. We have these visual objects, and with the visual objects, those are used to define my measurement plan.
You're basically just pointing and clicking on what it is you want to measure, and it's then going to the object and selecting it on the object.
Every object represents a dimension on the print. My print is my roadmap to report dimensions on a part.
All right.
And every object is completely independent, self-contained. True position, rather, is another great example. If I open up a true position and I want to report the true position of some holes, I'll come in here and ask to define a circle. This has its own datum reference frame, so I can come in and just start selecting what I may want to use for that datum reference frame. Maybe this top front surface, the top surface, and a side surface. It may have a tolerance of 200 microns, but accepting that it is completely an independent object. And actually, if I have 3 other holes, highlighting that, I can paint that same true position request onto these 3 other circles.
And by paint, you mean it's taking the same parameters you were looking for that hole. You're just saying, okay, apply all that same stuff to those, so you don't have to run through the same process over and over again for each hole.
Yeah. Yeah. If I open up the last one in the list there, it's using that same 200 micron tolerance, referencing the same datum reference frame.
Okay. All right. So it just saves you from having to do those same steps for every single hole if they're all exactly the same.
Exactly. It's a shortcut. Realistically, this is going to be a much longer part program with lots of objects in there. And actually, even with that, as I build this long measurement plan, a full layout of the part, I may want to start doing some management of that. The front face may be done in an operation. The top part might be done in a second operation. And instead of building different programs, I would have just one complete measurement plan and manage that product.
Got it.
And I would do that just by highlighting the entities that are done in a particular operation. And with that, I can come in and define what we call our mini plans. So this I might call, op 10. But again, these are completely independent. If I can highlight those, I can push them, move them around, and within my measurement plan.
So now that this is actually, we've created a measurement plan now. This is the...
Yeah, this is a measurement plan suitable for an arm.
Okay.
If I were wanting to go to a CNC machine, a CMM, there's a few things I would need to address. One of those, how do we navigate around this part? How do we go from one circle to another, and so forth? So within the Calypso software, what I'm going to actually come in here and I'm going to come into my CMM tabs, and across the bottom here, I have predefined different profiles set up for me. So I have a profile set up to connect to a ferro arm. I have another profile set up to connect to a Prismo type machine. Okay. And within that, if I connect to that, it's going to load the data for that Prismo. The size of the machine, what tooling, what probes are calibrated, and make those available for me to use.
Okay.
In preparing this measurement plan, to be run on a different machine.
Okay, so what you're saying is in that menu we just saw, you have all the different interfaces that Calypso supports, and you just bring down the machine, type of probes, that sort of thing.
Yeah, Calypso supports about 35 different machines and interfaces. I may only set up the ones I'm concerned about ever connecting to on the system.
Oh, so you could set up this plan to run on 2 or 3 or 4 different machines if there was some reason to do that.
Yeah, okay. And if companies do own 3, 4, 10 machines, they're all somewhat different.
Okay.
So you would prepare it that way.
Gotcha.
As I look at this, there's a couple things I need to address. One is when it comes to a CNC machine, what do we use to locate this part on that instrument? So we do it with what we refer to as a base alignment. And inside of there, I'm just going to define that I want to use this plane and this feature and this feature to define that alignment.
All right.
So I can accept that. The other concern I may have on a CNC machine is how do I actually navigate around this part? And what we have in Calypso is use a clearance cube. And this replaces all of those position points that we had in older other software. And again, the power of this ultimately comes to us, or the benefit is when we have these independent objects and we want to rearrange them freely, we really need Calypso to navigate how to go from one feature to another.
And by the clearance cube, this is just kind of a safety measure to keep the probe from crashing into other areas when it's moving from one position to another. Do I have that right?
Exactly. Okay. Yeah. We're gonna on the machine, we're gonna have to go from this top circle to the front circle, and someone's going to have to navigate to get from there to there. We might as well let the software figure that out for us.
Okay.
In Calypso here, the other thing that we're going to need to address, let me pull this out of the way here, is how do we actually assign the correct probe to each individual circle and plane that we had to measure. If we look at the arm here, the arm had a lot of flexibility. It had one probe that could access all this different geometry. On CMMs, we have a different tool, in this case, a scanning sensor, and I've actually got a star probe, prepared to measure that part. So, with that, sorry, I fell wrong menu here. I can pull up an editor. This is an editor that shows us all the different parameters about the geometry that we've extracted so far. And one of the items that I'm looking at is instead of using the ferro probe, I'm going to come in and use a star probe. And then from there, all the individual styluses need to be addressed. And I can kind of do that manually because I know this front plane needs to use the back probe. So I can come in and select back probe. But realistically, this list is going to be quite long. And this would be time consuming to address each individual one. So instead of that, what I'm really just going to do is use a tool in the software to automatically assign the correct stylus for each individual feature.
Okay.
So as I bring that up again, you can see it's gone through my list and automatically chosen the correct sensor.
So the software is based on what it knows about the probe and it knows about the geometry of the part. It can decide which part of that star probe to use to make a measurement.
Yeah, it's using some simple logic. Basically, it looks at the vector of the feature itself, and it looks at the vectors of all the probes you have available, and just assigns the correct probe to each one. So I'm just doing one last little edit here. All of this geometry was being told to execute in a manual mode. I'm going to prepare this to be run on a CNC machine, so another small edit to conclude that. But as it is, I now have a measurement plan, prepared to inspect what was initially built with an arm, now ready to be inspected on the machine.
Okay. And so we can take it over there, or is there any other steps? Or?
Well, there might be one last step here. We can actually highlight some of these and start simulating some of the geometry. Okay. So if I want to simulate this parallelism or perpendicularity, you would just highlight or the entire thing if you really wanted to. But I might highlight a particular characteristic that I want to report, and accepting that, it's going to come down here and so measure the actual part.
This is an actual simulation of what the CNC machine, the CNC CMM is going to do, how it's actually going to move the probe.
Yep, no, it's exactly. It's almost in real time, and it will move exactly as we're seeing it right here.
Okay.
Pretty good tool, because as that was running, and let me run it again here. There's a small collision happening in right about here.
Oh, okay, I see it.
Yeah, so
went right through the wall. Yeah, that's not going to work.
And fine here in the world of simulation. It's really not that big of a deal. Calypso does really try to address as much navigation as it can. It is software. It tries to automate everything. It does its best as software can do. It's still going to make a few mistakes.
Okay.
So the benefit of simulating is it identifies those mistakes. Actually, down in here, it'll go right to the actual feature with the collision.
Oh, so it actually detects that there was a collision and tells you, so that you can go in and fix it somehow.
Yeah, it does exactly. It does some logic. It says solid, meet solid. That's not good. So if I actually open this guy up, it's actually showing me the path that is following, and you can see it's probably not the best path that we have on there. A better strategy probably maybe use that back probe. And maybe just scan the front of the part here.
Sure.
So, I can just tell it, use the back probe. I'll go into the strategy of this plane. I'll delete that existing polyline that was created. And I can just go in and create my own. And I'll say, I want you to go from here to here, here to here. Do that with an arcing motion. Kind of exit there. So I can actually, in the software, quite efficiently alter the program itself. So again, being object driven, I'm debugging a very specific part of my program. If this was a scriptic type language, it'd be challenging to know, how to rerun a particular instance. If it's scriptic in nature, normally I'd just say, well, start from the finish, start at the beginning and go to the end.
Sure.
Again, time consuming. Right here, all I'm going to do in Calypso is just highlight the actual parallelism that I'm actually debugging, and just run that. Okay, so now you'll see it'll come down and use that back probe, measure just a part of it.
So it ran the path that you just created, and it used the different part of the star probe that you just identified.
Exactly.
Okay. So collision fixed.
Yep. And normally I would simulate the whole program top to finish before I would go to a CNC machine, but we're pretty comfortable here.
All right. So now you're ready to put this on a CMM?
Yeah. Okay. Yeah. All I would need to do is save it and close it. Take my part.
Okay. Well, why don't you take your part over to the CMM, and I'll just tell our viewers a couple things here. So once again, remember that at any time during the show, send your questions to techno-live@qualitydigest.com. We'll answer your questions live on the air. I see we actually have a couple questions that already came in. They happen to be related to the CT, so we'll hold those off. We'll hold those questions off until we get over to the CT demo. So remember, techno-live@qualitydigest.com. And I see that Scott is back over at the machine. So Scott, go ahead and take it from here.
So I've come over here. We have a ZEISS Contura G2 model And I've just put my part here in a fixture, and I'm going to ask Mick here to just manually align the part. The CMM needs to obviously know where this part is before it's executed. So if you look in the software, similar to the arm, it's actually prompting Mick here what surface needs to be measured to do this alignment. So as Mick goes through this, it's going to take about a minute or so. Dirk, this might be a great time to answer some of the questions that are coming in.
Yeah, sure. We've already got some questions coming in on the Calypso software. And as I said, we also have some questions coming in on CT, but we'll hold off on those. So the first question here is from William in Ohio. He wants to know, when you've upgraded with Calypso, can I still run my original OEM software?
Yes, it's a good question. Within ZEISS, with Calypso, we're not retrofitting machines. We're not changing controllers or rescaling or cutting wires. We're not damaging the CMM in any way. We're just simply adding Calypso to whatever the existing setup is. So if they're running a particular software, they could just run that and continue running it, in parallel with Calypso and use whatever their software of choice is.
Okay. Now,
at the time,
when you say upgrade, is that loading Calypso on their computer that's on their legacy machine, or is this a completely new system, or what's the deal?
It could be not always working well because the older legacy softwares are running in DOS or something older. Calypso is running in Windows 7 or XP, and we typically just have a separate computer installed.
Okay, so they basically don't have to touch anything about their old software or old computer. You're basically, if you need to, hook up a new computer with the Calypso on it.
Yeah, every controller has a different type of connection. Some of them are serial connections or a LAN connection. So the cable itself, we could put an AB switch to jump back and forth.
Okay, we have another question here from Xavier in California. Who calibrates the machine after it's upgraded with Calypso? What is he? First of all, what's he mean by that?
Probably the concern there is the data, the correction data usually, or not usually, but sometimes resides in the operating system.
So the volumetric error correction stuff?
Yeah, the correction data. So it may actually be in the software. The software does often more than just prepare measurement plans. It is also managing the correction and the accuracy of the machine. So the question is who calibrates it. ZEISS, we are very flexible at that. We have the ability that if a customer wants to use the original OEM to calibrate the machine, or a third party, or whoever they're comfortable with, that's possible. Or they can actually even use themselves to provide that calibration. We do our own calibration with the Calypso product. We won't be able to calibrate the system in the other machine. Okay.
See, we have one more question here. This is from Jeff in Washington. This is a DME I++ question. Is Calypso using the DME I++ protocol to interface with other CMMs? And remind us what the DME I++ is.
DME I++ is a protocol standard that controls the communication between the software and the controller.
So it's a much more lower level.
It's just a communication protocol to simplify it. Okay. Calypso is I++ compliant. If a customer has a request, we could connect via the I++ protocol. But our success has mostly been just with direct interfaces to the controller and just communicate directly.
Okay. So let me see. We got another Calypso question here. This is Joseph from Santa Clara asks, what kind of reporting and exporting functionality does Calypso offer?
Quite a bit. We have some newer products called Flex Reporter that has a lot of graphical tools as far as the graphical side. For exporting, it can comma separated values, maybe the most common text files, PDF files, and you can store all the reports.
So if you needed to store, if you wanted to export the data for purposes of maybe running an I don't know, Minitab or something like that, some statistical process control software, you could do that, and
Calypso,
not a big deal.
Yeah, Calypso has about 15,000 seats out in the market. Okay. All the major statistics statistics software developers have links and connections to Calypso.
Okay. Looks like that's all the Calypso questions for right now. So looks like we're set up here.
Yeah. Mick aligned the part itself. He's probably left me to just turn it on here. But what you're going to see here as it runs is basically the same thing that we just did in the simulation. And this is going to measure the top planes and so forth, create that datum reference frame, and then start measuring the circles. So as that's running, I'll kind of conclude what we're doing here. I've taken a part, created a measurement plan with Calypso on the arm, at least manually up front, did some minor edits to that, brought it over here to a CNC machine and executing the same measurement plan with that. So I'll thank you with that, and I'll send it back over to Dirk.
I'm back over here with Raghu Bogoraju. He is an applications engineer with Carl Zeiss Industrial Metrology, and Raghu is going to tell us about the Metrotome and CT scanning. So Raghu, what do we got?
Metrotome is a very unique measurement device that uses X-ray technology to measure parts. Traditionally, CT systems have always been utilized to do a lot of non-destructive testing, to look inside the parts, to look for cracks or voids. But with Metrotome, you also have the added advantage that we built it from ground up as a true measurement device. It's a perfect fusion of two amazing technologies, metrology and tomography, hence the name Metrotome. So now you have this amazing ability to not only look inside the parts, but also measure extremely accurately both external and internal features. That gives us a lot of different advantages, and it opens up a lot of different doors to do different kinds of analysis. So I'm going to show you guys what Metrotome is all about, explain a little about X-ray technology, and actually scan a part for you guys today.
Oh, terrific. Okay.
So, okay, let's take a look at the system.
Okay.
And
so I can open the door here,
yep,
right?
Please go ahead.
So that's one of these.
That'll be the one on the right.
Door. Okay. Raghu, has anybody ever mentioned that the Metrotome looks amazingly like the shuttle from the original Star Trek program?
Yes, they have.
Just saying. Look,
we can beam someone up.
We can
today.
beam somebody out, or you can beam through them, as a matter of fact.
Exactly.
Okay.
So let's take a peek inside. The basic architecture of the CT system is you have an X-ray system, you have a rotary table, and you have a detector.
So the X-rays come out of this side of the machine and go across through the part into the detector on that side.
That's correct.
Okay.
So the X-rays come out in shape of a cone beam, and you basically put the part as close to the apex of the cone as possible to get the maximum magnification. And let's scan something for you today.
Okay.
And as you can see,
a very technical product sitting on here right now.
Exactly. I thought we'd do something fun. I have a walnut for you guys to let's peek inside the walnut. And
a very fancy fixture as well. I like that.
That's correct. We use expanded polystyrene or styrofoam. Basically, what it does is it is so low dense.
This is you're saying the styrofoam here is the fixture.
Yes.
All right.
The styrofoam is our fixture.
Okay.
So it blows through the styrofoam. X-rays go through the styrofoam, and you don't see it.
So the fact that the styrofoam is actually sticking up in front of the walnut there isn't really going to affect it at all. Okay.
It basically doesn't affect the scan at all.
Please close the door here. All right. Shuttle doors closing. Right. I know you guys don't watch Star Trek, sure, right? Yeah.
I'm going to start the scan.
Okay. And actually, we already, if I can, right now is probably a good point. Somebody already has a question here about Lance from Lamb Research wants to know, what is the accuracy of computed tomography?
The stated measurement accuracy of Metrotome is 9 plus L over 50. So if you have a 50 millimeter part, measurement uncertainty is plus or minus 10 microns.
Okay.
In the world of CT, the most important things are a combination of size and density. So as long as you have enough energy to penetrate through the part that is in front of the X-rays and the part can physically fit inside my machine, I get a good image on the detector. What makes the Metrotome a lot more unique is two different things. The two main factors that are involved during any CT scanning is the data acquisition and the data reconstruction. The data acquisition stage is very important because how you collect the data, how the signal gets collected on the detector drives how accurate your data set is. So with ZEISS, we have the ability to use the same guideways, the same scales, and the rotary tables that are used on our high precision CMMs. to avoid most of those problems that normally happen during CT scanning.
Okay.
The second stage is the data reconstruction stage. That is where you basically define where the true edge for your part is. I have a little artifact to illustrate what edge definition is and what we do to get accurate data sets. So if you kind of look at this artifact, it's a stepped cylinder artifact. So as I have a hole that goes all the way down into the part, so the inner diameter of that hole would not change even though I have varying material thicknesses. But X-rays look at it slightly in a different way. So as X-rays go through, let's say, the thickest layer at the bottom, they have a different signal on the detector.
Okay.
But at the top, there is less material, so I have a different signal. Even though the material is of the same density, based on the path length, I have different kind of intensities that are collected on the detector. So when you try to calculate or extrapolate an edge based on those grayscale values, you have different values. You could use an average value all over the part to compute where the edge is, but that doesn't give you, again, an extremely accurate edge. So what we at ZEISS do is have our own internal algorithms during the data reconstruction process that goes into every one of these individual pixels, or what we call voxels, and actually find the true edge for the part. That is what that gives us the best accurate data sets that come right off the machine. So the data is ready to do any calculations when it comes off the system. So there is no scaling, there is absolutely no converting it into any other formats.
Okay. Before we get further into this, run us through real quick basically how CT works. I mean, what was kind of the principle behind it?
I have once I started a scan, I have actually a small video that shows what happens during the scanning. So if we can clip to that video. So as you can see, a transparent view of the system. You have three major components inside the system. So you have an X-ray tube, you have a rotary table, and you have the detector like you saw earlier. So now we place the part on a piece of, again, a styrofoam. The door closes, the X-rays move into the field of view, the part moves into the field of view of the X-rays, and it does one 360-degree rotation. So at every single step, you're collecting a bunch of 2D projections.
So it's like a bunch of 2D X-rays.
Exactly.
Okay. All right.
So all those 2D X-ray projections are then reconstructed into a 3D data set.
Okay.
So now you have a data set that has both internal and external geometry associated with it.
Okay.
Okay. Now we have this data set, so what do you want to do with this data set? So let's talk a little bit about the different kinds of applications that we do. So I'm going to show you two different softwares today that we primarily use in-house to solve a lot of these problems. The first software I'm going to show you is, again, Calypso, that my colleague Scott just demoed earlier. Calypso drives the measurement side for the CT data as well.
Okay.
So irrespective of what the hardware is, the end software that we use to do all our metrology applications is Calypso. So if you pay close attention to my monitor, I'm going to talk a little bit about Calypso that my colleague Scott basically talked about. So I have the same part that he used to measure using the ferro arm and the CMM. I scanned the part on the CT system, and I used the same measurement plan that he built to run against the CT data.
Okay.
So Calypso is software that basically runs all our products. So I can take the same measurement plan that is designed on a totally different sensor and use to run it against my Metrotome output.
Okay.
The only difference now is instead of the points coming from a probe or an optical sensor, they come off a CT system.
Sure.
So let me read in my CT data set, and before we even venture into sitting down and building a measurement plan, I can very quickly now overlay this on top of my CAD file and do kind of a first article type inspection. So I can color.
This is the scan, just to back up a little bit, this is the same measurement plan that was created on the ferro arm, measured on a CNC CMM, and now we've used that same measurement plan to control the Metrotome.
Exactly.
To take the same data. Okay.
Exactly. Right. So if
now we're overlaying that data on the CAD file.
On the CAD file, and very quickly finding out how the part looks like overall, what the deviations to nominal geometry is. If I click at certain locations, it'll tell me what the deviations to CAD are based off those locations. So let's quickly run some of the characteristics that Scott built.
Okay, so now we're running the measurement plan.
We're actually running the measurement plan, and those arrows simulate the locations at which I'm actually collecting the data.
So the measurement plan that was created on the Faro arm, then used on the CNC CMM, is also being used now on this data here that was created from the Metrotome.
Exactly.
Okay. Well, while that's running, I know that'll take a couple minutes to run. Let's we got a couple more questions coming in here. Are there any types of parts that are not ideal for CT scanning?
Again, like I explained earlier, in the world of CT, the two most important things are size and density. So as long as I have enough power to penetrate through the parts, I get a good signal on my detector. So let's say if I put something like stainless steel in front of a 225,000 volt system, the X-rays won't have enough energy to penetrate through a part like that. So I wouldn't get a good signal. So the 225 kV system that Metrotome is primarily used for a lot of injection molded plastic parts, small stainless steel, small aluminum parts, magnesium parts, and stuff like that. So it's not just the density that influences it, it's also the size. So it's always a combination of size and density that drives that equation.
Okay. I got another question here from, this is also from William. He says he has a small facility and no real place to put, I guess what he's saying, no real place to put a separate piece of equipment. Does this need to be in a special room? Is the X-ray technology safe?
As you can see, it comes with a nice clamshell design. It's basically well protected. It's got a lead cover that protects the X-rays from escaping out. It is built according to the standards that FDA requires for all X-ray systems to be run at. And we basically have it in our demo room, so you don't have to build any special rooms or to surround it. The state of depending on the state that we install, the Department of Health has to certify these machines for use. So that is what drives the certification process.
Okay. So, but like you said, no special room. As long as you got a footprint for it. Okay, and people can, obviously, we're doing this, we're standing right next to it, there's no clearance area you have to worry about.
Exactly. The material that we use to generate X-rays is tungsten. So unlike some other elements, tungsten does not decay over a period of time. So there is no residual radiation left in the atmosphere. So as soon as I hit the X-rays off, I can basically open the door and there is no radiation leakage.
Okay. Looks like your
looks like my measurement plan is done, and as you can see, in about 2 minutes, it ran through the entire program, collected the data, and from now you have the full availability of Calypso's power. So I can go in and, like my colleague explained, convert these into Excel spreadsheets or any statistical softwares to do any kind of analysis from now on.
Okay.
The second software that I'm going to show you guys today is called VG Studio Max. It is a very powerful tool for visual analysis. I have this overmolded medical part that is it's a good example that illustrates the true power of CT.
If we can get a tight shot, okay, thank you. So this is a plastic part. I see there's an outer shell, and it looks like some sort of another part that's on the inside, right? So this is an inserted part?
It's an inserted part.
Okay, so two different pieces of two different materials.
Two different materials in an assembled state.
In assembled state, okay.
So if someone wanted to measure these in an assembled state, normally the only way you could do it is actually cut it and measure internal features. Okay. But with CT, you have this unique ability to actually go in now, and if you pay attention to my monitor, I can virtually go in and separate the materials based on their size and density. So if you look at my little histogram here, I have different peaks and valleys that drive they're basically a combination of size and density.
Okay.
So as I drag my little handle into different materials, I can segment them out. So right now, I can remove the outer plastic layer and focus just on the internal plastic. So I'll take a second for the rendering algorithm to complete.
So what you're saying is basically it's looking, doing this manually using the histogram, you're kind of selecting which opacity you want to look at. Okay.
Exactly, which opacity I would actually want to focus in on.
Okay.
And I also have the ability to virtually now slice through the part. So I can cut through the part just like I'm cutting it normally on a CNC machine so now I can go into any 2D projection and kind of walk through the slices. As you're walking through, as you can clearly see, there are some really large voids inside this part. So not only were we able to measure these parts in an assembled state, we were also able to tell our customer that there is a lot of porosity from in their injection molding process. So I can now go in and calculate or compute the volume of these voids and actually tell them or tell their molding engineers how much material they're actually losing per part.
So all those little dots I'm seeing,
all those little dots
those are voids.
Those are voids inside the part, and I can compute them based on their volume.
Okay.
So, and as I'm walking through the part, if I see something critical, I can quickly mark it and actually clip it. And as I clip it, it does a clip-in plane on the 3D data set. So now we can zoom in to that location and investigate it further. So now you have the ability to kind of peek inside your part.
Okay.
In
That's
whatever
great.
direction. So I can go in and look inside different components, segment them out based on their density. So it opens up a lot of different options. So with CT now, with one scan, I have the ability to tell the design engineer very quickly how good or bad their parts are against their nominal data set. I can tell their injection molding guys whether their wall thicknesses are good or they have voids inside their part. I can convert this into a different format, let's say an STL format or an ASCII point cloud file, which they could use to reverse engineer these parts. And take it one step further, I can create models that can be easily used to do finite element analysis or any kind of CFD analysis. So with just one scan, the different departments inside a company can use this technology to avoid a lot of bottlenecks in their production process.
Now, how might this be used in reverse engineering?
So, for example, if the customer wanted to extract these separate components and wanted to build CAD files for this, so now I can separate these two segments out and give them STL files, which they can use to create CAD files.
So you could actually extract the data for each of these pieces of plastic separately. And they could create...
From an assembled condition, I can segment out different components and give them individual STL files which they could use to reverse engineer.
Now, I'm assuming that what we're talking about here, it really depends upon this insert, in this case, being of a different type of material, right? If it was the same material, you wouldn't see the difference between them, right?
Again, it's always a combination of size and density.
Okay.
If I had very little of one material and a lot of the other material, then yes, I would have a different grayscale value associated with it.
Yep.
So as you can see, one has a lighter shade of gray and the other one has a darker shade of gray based on their densities and sizes. So I can easily extract those out. Okay.
We got a question here. Let me see. This is Leslie from Peachtree. Peachtree, Georgia, I guess, that's the town. How much training is necessary for operators to get up to speed on the Metrotom?
Not a lot. The interface that we use is extremely easy, user-friendly, and with any software, there's always a little bit of learning curve that is involved. But there are a few factors that drive the measurement: the amount of voltage, the amount of current, and what we call the integration time is basically how long you're exposing the part at each step as it rotates. So as long as you create a good balance based on the density and size of the part, you're good to go.
Okay.
So there's not a lot involved.
Okay. Let's see.
So now looks like our walnut's done.
Walnut done. All right. That's what I was waiting for.
So let's quickly read the data set in and take a look at the results.
So now we're going to look at this. This is the actual scan that we just finished. So, but while we were talking, it was scanning that walnut.
It's scanning and reconstructing the data in parallel.
Oh,
so there it is. So the same walnut that we just did.
It's amazing. It looks like a walnut.
Exactly. So you can actually see all the. So now I can go in and remove the shell and kind of cut through the part.
Oh, okay.
To actually look at the walnut inside.
Cutting down through it. All right.
And also extract some of this stuff. So let's go back.
Now, if you wanted to color code different densities, that's something that you could do? Okay.
Exactly. So let's quickly extract the actual walnut from the outer shell.
Okay, the kernel, okay. Oh, there it is.
So now...
So that's the actual...
That's the actual walnut inside the shell. Okay. So now I can, just like we did with the plastic components, since there are different densities, I can extract that out. So there you go.
All right.
And we have a little video for our viewers to
that shows how they...
That shows...
Right.
I actually stripped the actual nut from the shell, kind of walking through the part, gave it the actual nut a different color, and now you can see the internal.
Now I'm noticing that on the shell part, you're actually seeing even the structure of the inside of the shell.
Exactly.
Okay. Interesting. All right. Oh, that's very cool. Let's see. Okay, we've got some more questions coming in, and actually it looks like we have some Calypso questions as well. So Scott, if you can join us up here. Let's see. Oh, can I use the Calypso? This is from Jane. Can I use Calypso on the ferro arm to measure simple parts without a CAD file?
Yeah. Our demonstration used a CAD file. The benefit of CAD is it has all the inherited nominal geometry, so it's faster, but it's not a requirement. To do something simple, you're just creating those visual characteristics and calculating the same parallelisms, diameters. Instead of picking the model, you'd just be picking the part itself.
Okay. Can't seem to get back to this other question here.
Must have been a good one.
It must have been a good one. Oh, weird. There we go. How do you retrofit Metrology CMMs with a UC controller? Is that right? If it has an old ISA card.
The problem with a lot of the later Metrology machines is they used a proprietary ICA card for that communication. So Calypso does have an interface with those Metrology machines. What we use is a separate interface box, and we've taken what used to be an internal card to the original computer. That's just now an external card that we've developed. We own that device, and we communicate to the Metrology UCC controllers with that technology.
Okay.
So again, it's just a simple software upgrade. The customer can still go back and use his original Metrology software if he wishes.
Okay. See, another question came in here. This is for you, Raghu. Do you also provide measurement services for your customers?
We do sell these systems, and for customers who are very interested to get some service contract work done, we have 2 different service centers, one in Brighton, Michigan, and one in Irvine, California. So you could always send us parts, and we could do them for you.
Okay. Just checking my mail here again.
Business related?
Yeah, business related. Yeah. Okay. My wife, pick up the milk. I don't know. This is another Calypso question. Does Calypso support PMI? What's PMI?
Product manufacturing information. That's the technology and newer CAD files that they're adding characteristics like true position, diameters, and adding those dimensions inherited into the CAD file itself. But yes, to the question, CAD files with PMI coming from CATIA and Unigraphics, Pro Engineer, and we're also working on SolidWorks. Those come in, and if you were viewing Calypso earlier, all you're doing is double-clicking that characteristic, and they're creating the visual objects for you.
Okay. Let me see if we got anything else coming in here. A second. Getting kind of a slow connection. What do we got? Okay, well, you already answered this question. Another viewer wanted to know how accurate is the CMM, but I believe you already said it was 9
plus L over 50.
9 plus L over 50, so roughly 10 microns and 50 millimeters.
Exactly.
Okay, all right. A question I had myself, you had touched on edge detection, and kind of the problem with X-ray is that as you get closer to an edge, the edge gets thinner, and so the X-rays is kind of blowing through it, and that's what's making the edge hard to see?
It's not the fact that the X-rays are blowing through the part. Again, the amount of material that you have, as X-rays go through the part, they start losing certain amount of energy because they are interacting with the molecules of the part.
Okay.
So the signal that is collected in front of the detector is based on the amount of material that you put in front of it and the density of the material.
Okay.
So now, for a smaller sized edge, I get a very good signal because they go from one end to the other really fast. But I have more material at the bottom. In this case, now I get a weaker signal because they have to travel a longer path. But in case of this part, the step cylinder is a very good example because this internal bore diameter doesn't change from top to bottom.
Sure.
So even though the intensity of X-rays that are being collected at the top and bottom are different, our ability to go in and find the true edge is what drives or what creates the more accurate file.
Okay. I don't see any questions right now, and we've got a couple minutes left. Is there anything you guys wanted to add to either of your presentations? Anything maybe you didn't touch on?
That was it, I remember.
That was it.
Wow, that was really good. And you guys are really thorough. I mean,
thorough.
Man,
I think we covered it all.
It's like, that's
Well,
it.
do you want the walnut?
Yeah, sure, I'll take the walnut. And hey, it's not radioactive or anything,
It's
right?
not radioactive.
Right. That's cool.
There you go. This is from us.
Thanks. All right. And now I know what the inside looks like. Yeah. Okay. Okay, guys. Raghu and Scott, thanks once again for joining us. And thank you guys for joining us as well. If you still have questions, feel free to keep sending them to techno-live@qualitydigest.com, even though we're out of time right now. And I'm just making one last check, make sure nobody's come in. Okay. Even though we're out of time right now, if you do send in questions, we'll continue to pass them on to the folks here at ZEISS, and somebody will get back to you with any answers to your questions. So once again, Raghu, Scott, thank you for joining us here on the show today, and keep your eyes open, you guys out there, in your email for a survey that will come up asking for the quality of the content, quality of the broadcast itself, technical quality, and be sure to send those back to us because that really helps us to plan the shows in the future. So once again, thanks for joining us, and we'll see you at the next Technorazzi Live.